Something has been travelling toward our Sun for 1900 years. It left the inner solar system when Rome still ruled the world, and it has been moving through absolute darkness ever since, silent, frozen, and completely indifferent to everything humanity has built in its absence. Now it is almost here. Comet C 2026. A1 is about to plunge closer to the Sun than the Moon is to Earth, travelling at 557 kilometers per second. And the timing is, to put it gently, unsettling. A 7-ton fireball over Ohio, triple coronal mass ejections hitting Earth this week, and a Harvard professor asking whether this comet is connected to an interstellar object that just left our solar system. 2 scenarios are expected. It could become the brightest comet in years, or it could trigger something aimed directly at us. April 4th is almost here. Stay with me, because what happens next might change how you look at the sky forever. April 4th is not a threat. It is a question, the most precisely observed question a sun-grazing comet has ever asked our star. Subscribe and follow along, because we are not finished asking what the Sun is capable of, and based on this week alone, the Sun is clearly not finished showing us. Now let's get into this. Part 1. The claim nobody wants to say out loud. There is a rock older than the Roman Empire hurtling toward the Sun right now, and almost nobody's talking about it. Not because it isn't worth talking about, but because the people who understand it best are the most reluctant to say what it might mean. That silence, that careful, deliberate scientific quiet, is somehow the most unsettling part of this whole story. Here is what we know for certain. A comet designated C/2026A1, discovered by the MAP survey program, is on a trajectory that will carry it to within 161,000 kilometers of the solar surface on April 4th. To put that in perspective, the Moon is roughly 384,000 kilometers from Earth. This comet will pass the Sun at less than half that distance. It will be travelling at 557 kilometers per second. That is not a typo. 557 kilometers every single second. It will cross the Sun's corona, the outermost atmosphere of our star, and either survive that crossing or die inside it. And the outcome of that decision, made by physics and chemistry on a scale we can barely compute, could matter to every person on this planet. Let's be clear about one thing immediately, because the internet has a way of turning scientific curiosity into survivalist panic. This comet is not going to hit Earth. It is not aimed at us. There is no impact scenario. What there is instead is something more interesting and in some ways more unsettling than a simple collision. There is the question of interaction. C/2026A1 belongs to a family of comets called Kreutz sungrazers. These are objects that follow orbits carrying them on near-suicidal passes around the Sun, and they are the remnants of a much larger comet that shattered sometime in the ancient past. Most of them are small. Most of them die quietly in the corona, vaporizing without ceremony, observed only by solar telescopes and the small community of astronomers who track them. But this one is different in a few notable ways, and those differences are what have people quietly leaning forward in their chairs. The Sun is currently at or near the peak of solar cycle 25. Solar cycles run roughly 11 years, and at their peaks, our star becomes dramatically more active. It produces more sunspots, more solar flares, and more coronal mass ejections, or CMEs. A CME is essentially a massive eruption of magnetized plasma from the solar surface, a cloud of charged particles that can travel through space at millions of kilometers per hour. When one of these clouds hits Earth, it interacts with our magnetic field and can cause geomagnetic storms. Moderate storms produce spectacular auroras. Severe storms can disrupt satellite communications, damage power grids, and in extreme historical cases, have collapsed entire electrical infrastructure systems. The Sun, right now, is already doing this. Multiple CMEs have already struck Earth this week. Sunspot regions are actively flaring. The solar weather right now is genuinely measurably rough. And into this already churning environment, a comet older than most of recorded human history is about to plunge directly into the corona. The speculation, and it is important to say this clearly, it is speculation, not confirmed science, is that if this comet disintegrates inside the corona, the energy and material released could act as a trigger or an amplifier for solar activity. Not because comets routinely do this, they don't, but because at sufficient size interacting with already stressed magnetic field regions, there is a non-zero possibility of contributing to a disturbance that might otherwise not have happened, or might have happened later, or might have happened smaller. The scientists who study this are careful with their language. They use words like possible and could contribute and warrants monitoring. That careful language is not reassurance. It is the sound of people being professionally responsible while privately curious about something they cannot fully predict. There is also a timing coincidence that you either find meaningful or you don't, depending on your tolerance for pattern recognition. On March 17th, a fireball estimated at roughly 7 tons streaked across the sky over Ohio. The following days brought confirmed geomagnetic activity from multiple CMEs, and now, just days away, a comet that has been travelling for roughly 1900 years arrives at the one moment in its entire orbital history that coincides with peak solar activity and a period of unusually dense space weather events near Earth. You can call that a coincidence. Statistically, it probably is. But the universe has a way of making coincidences feel personal, and this one has a certain gravitational pull on the imagination. We are watching this in real time. April 4th is perihelion, the moment of closest approach. And between now and then, every solar telescope pointed at the Sun, every magnetometer on Earth, and a growing number of people who have heard just enough to be genuinely concerned are all waiting to see what happens next. The question is not whether something will happen. Something will definitely happen. The question is what kind of something, and whether the Sun, already restless, already active, already pushing electrical and magnetic energy toward our planet, decides to notice the visitor. That is the claim nobody wants to say out loud. Not that we're in danger, but that we genuinely don't know. And in the era of planetary risk assessment, we genuinely don't know is the most honest and least comfortable answer available. So let's talk about the timeline, because when you lay the events of the past 2 weeks out in order, the sequence has a rhythm that is difficult to ignore. Part 2, the timeline that feels too aligned. Something landed over Ohio on March 17th, and most people missed it entirely. A fireball, a meteor large enough to produce a visible multi-second streak across the daytime sky, entered Earth's atmosphere and disintegrated. Estimates put its mass at around 7 tons, and its explosive energy at approximately 0.37 kilotons of TNT equivalent. That sounds dramatic, but it is worth being honest. Events like this happen more often than most people realize. Earth is hit by small space rocks constantly. The vast majority burn up harmlessly in the upper atmosphere. What made the Ohio event notable was its visibility, its timing, and the fact that it arrived in the middle of a 2-week sequence of space weather events that, laid out in order, starts to feel less like random noise and more like a pattern. Here is that sequence. In the days around March 16th through 18, active sunspot regions on the solar surface launched a series of significant flares, and at least 3 of the resulting coronal mass ejections were directed toward Earth. The geomagnetic storm window associated with these CMEs was projected to run from approximately March 19th through 21st. During that same window, the Ohio fireball occurred, and sitting at the end of this sequence on April 4th is the perihelion of C/2026 A1, a comet travelling at 557 kilometers per second that will pass closer to the Sun than our Moon is to us. Now here is where intellectual honesty becomes important, because this is exactly the kind of sequence that the human brain is designed to find meaningful. We are pattern recognition machines. It is one of our greatest cognitive strengths and one of our most persistent cognitive weaknesses. When events cluster in time, our brains automatically search for a common cause, a unified explanation, a narrative thread. This is called apophenia, the tendency to perceive connections between unrelated things, and it is essentially the engine behind every conspiracy theory ever constructed, as well as behind many legitimate scientific discoveries. The difference between those two outcomes is evidence, not instinct. So let's apply that standard honestly. The Ohio fireball was almost certainly unrelated to solar activity. Meteors and the Sun do not communicate. The CME sequence was caused by sunspot activity that has been building for weeks, driven by the normal dynamics of solar cycle 25's peak. The comet has been on its current trajectory for roughly 1900 years, long before any of these events occurred. There is no demonstrated physical mechanism that connects these 3 phenomena into a single causal chain, and yet, and here is where it gets genuinely interesting, unconnected, and irrelevant are not the same thing. Multiple independent events can occur simultaneously and still overlap in their effects. A geomagnetically disturbed Earth entering a period of solar maximum, simultaneously receiving a sun-grazing comet into the corona, simultaneously detecting fireballs in its atmosphere, does not require those events to be causally linked for their combination to be scientifically significant. The convergence creates an observational opportunity unlike anything in recent solar science history. The media amplification of these events is also worth examining. When three things happen in proximity, a fireball, solar storms, and an incoming comet, the story spreads through a very particular kind of acceleration. Each event becomes evidence for the others. The fireball becomes a warning sign. The solar storms become preparation for something bigger. The comet becomes the trigger. None of this is supported by data. All of it is supported by narrative gravity, which is the tendency of stories to pull additional details into orbit around them. This is not a criticism of the people sharing the information. It is simply a description of how human beings process uncertainty, especially when the stakes feel existential. What the timeline does tell us legitimately is this. We are observing a rare clustering of space weather events during a period of solar maximum, and those events are arriving in a compressed enough window that distinguishing their individual signatures will require careful, precise scientific observation. The geomagnetic storms already recorded this week will affect the baseline against which any post-perihelion activity is measured. If something unusual happens on or after April 4th, separating that signal from the ongoing solar noise will be genuinely difficult, and sometimes the rarest events do not arrive alone, not because the universe is sending a message, but because when conditions align, when a star reaches peak activity, when a comet born from an ancient fragmentation event arrives on schedule, when Earth happens to sit in the path of an already energized solar wind, the combination of independent rare events can produce outcomes that none of them would have produced individually. That is not mysticism. That is compounding probability. And the compound probability here, while still low in absolute terms, is higher right now than it will be again for a very long time. The question is whether the comet at the center of all of this is as ordinary as it seems, because when you look at the data on C/2026A1 itself, a few details don't quite fit the expected profile. Part 3. The object itself isn't normal. Most sungrazers are discovered days before they reach perihelion, tumbling out of the darkness just in time to be watched and then lost. C/2026A1 was not discovered that way. The MAP survey program detected it in January of 2026, when it was still approximately 2 astronomical units from the Sun, that is roughly 2 times the distance from Earth to the Sun. For a Kreutz sungrazer, that is extraordinarily early. These objects are typically faint, small, and difficult to detect at that range. The fact that this one was found so far out either means it is unusually large, unusually bright, or both. And that early detection is the first thing that sets it apart from the hundreds of sungrazers that preceded it. Initial size estimates, based on brightness and reflectivity models, placed the nucleus at approximately 2.4 kilometers in diameter. That is a meaningful number. Size matters enormously for sun-grazing comets, not because larger comets are inherently more dangerous in an everyday sense, but because size determines survivability. A larger nucleus contains more material, and more material means more structural integrity when the comet plunges into a 2 million degree plasma environment. Later revised estimates brought that figure down to approximately 0.4 kilometers. That revision, a reduction of roughly 80% in estimated diameter, represents a significant uncertainty in our understanding of this object, and uncertainty about a comet entering the solar corona is exactly the kind of uncertainty that keeps solar physicists quietly attentive. For context, consider the comet Lovejoy, which executed a similar near-suicidal solar pass in 2011. Lovejoy was estimated to be around 200 meters across. It was supposed to be destroyed. Every model said it would vaporize in the corona. Instead, it emerged from perihelion scorched and dramatically diminished but recognizably intact, trailing a luminous tail visible to the naked eye from the southern hemisphere. The scientific community was genuinely surprised. Lovejoy had survived something that the prevailing models said it could not survive, and that surprise produced a wave of revised thinking about what sungrazers are actually made of and how they interact with the corona. C/2026 A1 has an estimated orbital period of approximately 1900 years. That means the last time this object was in the inner solar system, the Roman Empire was still standing. Augustus Caesar may have been alive. The concept of the telescope would not exist for another 16 centuries. Nobody was watching. Whatever happened during that perihelion pass, if this object even made a pass at that time, went unrecorded. We have no observational baseline for how this particular comet behaves near the Sun, because we have never seen it there before. The orbital period also raises a taxonomic question. Kreutz sungrazers are organised into subgroups based on their orbital characteristics. The known subgroups, designated by letters, have predictable orbital parameters derived from the original fragmentation of the ancestral megacomet. C/2026 A1 does not map cleanly onto any of the established subgroups. Its inclination, its period, its approach angle, they are close to the Kreutz family signature, but not quite aligned. Some researchers have proposed that it may represent a previously unrecognized fragmentation branch, a lineage that split off from the main family at a different time or under different conditions. That would make it scientifically novel in a way that goes beyond its upcoming solar pass. Why does that matter? Because if we are dealing with an object from an uncharacterized subgroup, our compositional models for it are even less reliable than usual. The material properties of a comet, the ratio of ice to rock, the structure of the nucleus, the volatility of its surface compounds, all influence how it will behave inside the corona. If this object is from a lineage we have not studied, our predictions about its disintegration timeline, its outgassing behaviour, and its potential to produce plasma disturbances are built on assumptions that may not apply. So we have a comet that was discovered unusually early, whose size has been revised dramatically downward, whose orbital period suggests it has never been observed at perihelion in the historical record, and whose classification within the Kreutz family is uncertain. None of these facts individually constitute an alarm. Together they constitute a very strong case for paying close attention. Is it stronger than we think, and therefore more likely to survive? Or is it weaker than the early estimates suggested, and therefore more likely to fragment dramatically inside the corona? The answer to that question will shape everything that comes after it. Part 4. Survival isn't binary. Here is a misconception that shapes almost every conversation about this comet, the idea that it will either survive or it won't, and that only one of those outcomes is interesting. That framing is wrong, and the reality is considerably more fascinating. Comet behaviour during a solar perihelion pass is not a binary switch. It is a spectrum with at least 4 meaningfully distinct outcomes, each producing a different observable result, each carrying different implications for what happens to the Sun and to us. The first outcome is pre-perihelion breakup. This is exactly what it sounds like. The comet begins to fragment before it even reaches closest approach, the nucleus splitting and dispersing into a spray of smaller objects and debris. At this point, the drama ends early. The individual pieces are too small to produce significant plasma interaction, the visual spectacle collapses, and astronomers note the event in their records and move on. This is the most common fate for small Kreutz sungrazers. The second outcome is what solar observers call a headless comet. The nucleus disintegrates during or just before perihelion, but the debris cloud and the coma, the envelope of gas and dust surrounding the nucleus, persist long enough to produce a visible tail that continues moving along the original orbit. From Earth, it looks like a comet. There is a bright streak. There is a tail. But there is no central object anymore, just a loose cloud of vaporizing material following the ghost of a trajectory. This outcome can still produce impressive visual effects and has interesting implications for plasma interaction in the corona. The third outcome is medium survival. The comet emerges from perihelion diminished but functionally intact, producing a visible tail that can be observed from Earth over subsequent days or weeks. This was roughly the Lovejoy scenario. Depending on the remaining mass and activity of the nucleus, this could produce a comet bright enough to observe with binoculars, or in an optimistic scenario, with the naked eye in evening sky. The fourth outcome is extreme survival. The nucleus passes through the corona at full or near full mass, emerges with significant remaining volatile material, and produces an outgassing-driven display of extraordinary brightness. Historical precedent for this exists. The comet Ikeya-Seiki in 1965 reached an estimated magnitude of -10, roughly 25 times brighter than Venus at its brightest. it was visible in daylight. Multiple historical accounts from pre-telescopic eras describe similarly spectacular comets that are now attributed to Kreutz family sungrazers. Some researchers have assigned these historical sightings magnitudes in the range of -10 to -15. We tend to dismiss those accounts as exaggeration, but Ikeya Seki reminds us that the physics actually allows for them. The brightness scale used in astronomy, the magnitude system, is counterintuitive for non-specialists. Lower numbers mean brighter objects, and negative numbers mean very bright objects. Venus sits at around -4.9. Ikeya Seki was estimated at -10. Some projections for C/2026 A1 in an extreme survival scenario reach into very high negative magnitudes. Those projections are almost certainly too optimistic because they assume a fully intact nucleus of the original estimated size, which the revised estimates suggest we probably do not have. But even a partially degraded nucleus surviving perihelion could produce something visible in daylight, and that is not a trivial statement. Here is the genuinely counterintuitive insight. The most spectacular visual outcome might come not from perfect survival but from partial fragmentation. A nucleus that breaks apart in the outer corona, producing multiple active fragments all outgassing simultaneously, can create a broader, more luminous display than a single intact body. The tail of a fragmenting comet can extend across 10 to 30 degrees of sky under the right conditions. That is a dramatic natural light show, and it comes precisely from the object failing in the most interesting possible way. The informal nickname Easter Comet has started circulating in amateur astronomy communities, reflecting the timing of perihelion just before Easter Sunday. Whether that nickname ever becomes more than wishful thinking depends on what happens on April 4th and in the days that follow. The comet that arrives as a rock may leave as a light show. The question is what it leaves behind in the sun along the way. Part 5. The CME question. Let's talk about what a coronal mass ejection actually is, because the term gets used constantly in space weather discussions, and it deserves a clear, honest description. Imagine the sun sneezing. Not metaphorically, almost literally. A region of the solar surface, stressed by tangled and intensifying magnetic field lines, suddenly releases an enormous bubble of magnetized plasma. This is not a gentle release. The bubble can contain billions of tons of material and travel at speeds between 300 and 3,000 kilometers per second. It expands as it travels, so by the time it reaches Earth, roughly 1 to 3 days after leaving the Sun, the cloud is vastly larger than the planet itself. When it arrives, it collides with Earth's magnetosphere, the protective magnetic field that surrounds us, and depending on the orientation and intensity of the incoming field, it can compress and distort the magnetosphere in ways that drive electrical currents through the upper atmosphere and, in severe cases, through the ground itself. Those ground-level currents are what damage transformers, knock out satellites, and in the worst historical scenarios, collapse power grids. The Sun produces CMEs regularly. Near solar maximum, it can produce several per day. The vast majority miss Earth entirely. A significant fraction pass by without producing major effects. But the ones that do connect, that hit Earth's magnetosphere at the right angle, with the right field orientation, can produce effects ranging from beautiful aurora displays to multi-day communications disruptions to, in extreme scenarios, events that make modern infrastructure genuinely fragile. Now here is where the comet becomes relevant, and where the scientific community becomes notably careful with its language. The standard CME trigger is magnetic reconnection, a process where magnetic field lines of opposite polarity approach each other, snap, and release enormous energy. This happens on the Sun constantly. It does not require outside assistance. The Sun is perfectly capable of generating every CME it has ever produced entirely through its own internal dynamics. The controversial question, and it is controversial because the evidence is genuinely ambiguous, is whether external material entering the corona can interact with magnetic field regions in ways that influence CME initiation. Can a comet disintegrating in the corona deposit enough material in enough concentrated form to trigger or amplify a magnetic reconnection event that might not have happened at that moment or at that intensity on its own? In 2011, a small sungrazer entered the corona and disintegrated. Around the same time, a CME erupted from a region of the solar surface near the comet's trajectory. Researchers looking at the SOHO and SDO telescope data noted the timing. Some proposed a possible connection. The mainstream scientific consensus held that the CME was coincidental. The Sun was active, CMEs happen. The timing was not sufficient evidence of causation. That consensus position is almost certainly correct, and yet the event was never fully resolved to everyone's satisfaction, and the question of whether it was truly coincidental has never been definitively closed. The Harvard astrophysicist Stephen Burns has raised a version of this hypothesis in the context of C/2026A1, suggesting that a sufficiently large impactor, or sufficiently large disintegrating comet, interacting with already stressed magnetic field regions could contribute to solar disturbance. He is careful to frame this as a hypothesis requiring observation, not a prediction. But the framing matters because it comes from someone with institutional credibility and a publication record, not from an anonymous social media account. Here is the uncomfortable layered probability at the centre of this. For a comet-triggered major CME to occur, multiple low-probability conditions would need to align simultaneously. The comet must be large enough to deposit significant material. The disintegration must occur in or near a magnetically stressed region. That region must already be close to reconnection threshold. The resulting CME must be directed toward Earth, and the Earth must be in a geometrically vulnerable position when it arrives. Each of these conditions has a relatively low probability. The compound probability of all of them occurring together is lower still. But here is what nobody wants to say out loud. We are currently sitting in a solar maximum. The Sun is already generating CMEs. The existing solar wind is already energized, and an object whose composition and structural integrity we do not fully understand is about to enter the region of the Sun most directly connected to that activity. The Sun does not need help to erupt. It has been erupting for 4.5 billion years without any assistance from passing comets. But the question of what happens when it gets some, when an ancient rocky visitor arrives at exactly the wrong moment in the wrong place, is one that our instruments will be watching very carefully on April 4th. Part 6. Inside the solar corona. The kill zone. The corona is not what most people imagine when they think of the Sun. When you picture the Sun, you probably picture a bright yellow ball, the photosphere, the visible surface, the layer we see in photographs. The corona is above that. It is the Sun's outer atmosphere, and it begins where the visible surface ends and extends outward for millions of kilometers into space. It is the region visible during a total solar eclipse as the pearlescent halo surrounding the darkened disk. It is beautiful, it is ancient, and by almost any standard relevant to the survival of physical objects, it is completely and utterly lethal. The temperature of the corona is one of the genuinely strange facts in astrophysics. You would expect the temperature to decrease as you move away from the solar surface, the way temperature drops as you climb away from a heat source. Instead, the corona is hotter than the surface by orders of magnitude. The photosphere, the visible surface, is approximately 5,500 degrees Celsius. The corona reaches temperatures between 1 and 3 million degrees Celsius. Nobody fully understands why. This is called the coronal heating problem, and it remains one of the open questions in solar physics. The leading explanations involve magnetic wave energy and reconnection events, but a complete unified theory does not yet exist. For a comet entering this environment, the temperatures are only part of the challenge. The corona is also permeated by magnetic fields of extraordinary complexity, tangled, braided, constantly reorganizing structures that store and release energy in ways that drive all of the dynamic phenomena we associate with solar activity. Flares, CMEs, filament eruptions, coronal loops, all of these emerge from the behavior of these magnetic structures. A solid object entering this magnetic environment is not just entering heat, it is entering a contested electromagnetic landscape that exerts forces on any electrically charged material it encounters. When a comet like C/2026A1 approaches the Sun, several destruction mechanisms operate simultaneously. Thermal vaporization begins when solar radiation heats the surface to the point where volatile materials, water ice, carbon dioxide, other frozen compounds, sublimate directly from solid to gas. This produces the coma and tail that make comets visible. As the comet moves closer, the heating intensifies dramatically, moving from surface vaporization to wholesale destruction of the nucleus itself. At corona grazing distances, the temperatures are sufficient to vaporize rock. Tidal forces present a second mechanism. Gravity decreases with distance, and at very close approach to a massive object, the gravitational pull on the near side of a body significantly exceeds the pull on the far side. This differential, called a tidal force, can literally pull an object apart if the structural integrity of the material is insufficient to resist it. For a comet nucleus, which is essentially a loose aggregate of rock, ice, and organic compounds, loosely held together by its own weak gravity, tidal forces at near perihelion distances can be sufficient to induce fragmentation. A third mechanism involves the comet's own outgassing. As volatile material vaporizes from the surface, it does not evaporate evenly. It erupts in jets from specific regions where volatiles are concentrated or exposed. These jets exert force on the nucleus, spinning it, torquing it, sometimes tearing fragments away. At sufficiently close solar approach, the outgassing rate can become violent enough to be structurally destabilizing. What makes this scientifically extraordinary, rather than merely destructive, is the nature of the interaction. This is not burning, in any conventional sense. There is no oxygen in the corona. What is happening is a transition of matter through plasma states under electromagnetic forcing, and the products of that transition, ionized gas, charged particles, metallic vapor, are observable by solar telescopes in ways that tell us about both the comet's composition and the corona's response. Every atom that this comet surrenders to the Sun is a data point. If the comet fragments cleanly, and the instruments are recording at full capacity, April 4th will produce more information about cometary composition and corona interaction than any single event in the history of solar observation. We are watching matter become energy under conditions that do not exist anywhere else in the local universe. The comet that arrives as an ancient frozen relic of the early solar system will leave as radiation, plasma, and light. The question of how that transformation affects the Sun's already charged and restless magnetic field is what the entire solar physics community is quietly waiting to find out. Part 7. The 2011 event that still isn't fully explained. In 2011, a small sungrazer passed through the solar corona and vanished. This happens fairly regularly. Hundreds of Kreutz family fragments make this journey every year, the vast majority of them too small and too faint to survive the encounter, detected only by SOHO's coronagraph and noted in catalogues that most people never read. They enter, they disintegrate, they are gone. The Sun does not notice. The scientific community notes the event and moves on. This is the routine, unremarkable fate of most sungrazers, and there is nothing about it that warrants extended attention. What made the 2011 event different was not the comet. It was what the cameras caught after the comet disappeared. To understand why that matters, it helps to understand what the Solar Observation Network looked like by 2011 and what it was capable of recording. The Solar and Heliospheric Observatory, SOHO, had been in continuous operation since 1995, positioned at the gravitationally stable point between Earth and the Sun, where it maintains an unobstructed view of the solar disk and the surrounding space without ever passing through Earth's shadow. Its coronagraph, blocking the solar disk to observe the surrounding corona, had by 2011 accumulated 16 years of continuous solar monitoring, a dataset of unprecedented scope covering thousands of coronal mass ejections, solar wind structures, and cometary passages across the full range of solar cycle activity. SOHO did not just take pictures. It recorded the Sun's behaviour in a form that allowed researchers to go back and examine any moment in that 16-year record in detail, comparing events, identifying patterns, and constructing statistical baselines for what normal solar behaviour looked like under different conditions. Alongside SOHO, NASA's Solar Dynamics Observatory had been operating since 2010, adding a capability that SOHO's design could not provide. SDO was built to observe the solar surface and lower atmosphere across multiple wavelengths simultaneously: visible light, ultraviolet, extreme ultraviolet, and X-ray, at a cadence of one complete set of images every 12 seconds. That temporal resolution was transformative. It meant that dynamic events on the solar surface, which can develop and evolve on timescales of minutes, could be tracked in essentially continuous detail rather than reconstructed from widely spaced snapshots. The magnetic field structures driving flares and coronal mass ejections, the plasma flows in active regions, the thermal signatures of developing instabilities, all of these became observable in real time rather than inferable after the fact. When the 2011 sungrazer made its approach, both instruments were watching, recording, and storing data at full capacity. The comet's behaviour in the corona was unremarkable by sungrazer standards. It entered the outer corona on the approach trajectory expected from its orbital parameters, began the disintegration process that the corona's extreme environment initiates in any object insufficiently massive to resist it, and tracked along its path toward perihelion in the way that hundreds of its predecessors had done before it. The nucleus fragmented, the debris dispersed, the coma and tail that had been visible in SOHO's coronagraph faded as the material vaporized and ionized into the surrounding plasma. Standard sungrazer behavior, observed and catalogued, another entry in the long record of Kreutz family members meeting their end at the Sun. And then, within hours of the comet's passage through the corona, a coronal mass ejection erupted. It erupted from a region of the solar surface in the general vicinity of the comet's trajectory. The timing was close enough that researchers examining the SDO and SOHO data in the days following the event noticed the apparent correlation and began asking the question that the data raised but could not answer. Several published analyses noted the temporal relationship between the sungrazer passage and the CME eruption. The papers were careful, as papers on contested questions tend to be, hedged with appropriate uncertainty language and explicit acknowledgement of alternative explanations. But they were published. The question was in the literature, and the question, once in the literature, had a way of remaining there regardless of whether the mainstream consensus found it convincing. The mainstream interpretation settled, relatively quickly, on coincidence. The Sun was active in 2011. Solar cycle 24 was past its minimum and moving toward maximum, producing regular flaring and CME activity from multiple active regions distributed across the solar surface. A CME erupting from a region near the comet's trajectory during a period of general solar activity proved nothing about causation. Correlation is not causation. The comet was small. Estimates placed it at perhaps a few tens of meters across at most, a fragment so minor that the physical mechanism by which it could influence a solar eruption of CME scale did not resolve into anything convincing under scrutiny. The conclusion, stated with the careful professional hedging that contested scientific questions attract, was that the CME was probably unrelated to the comet's passage. That word, probably, is doing an enormous amount of work in that sentence, and it is worth stopping to examine exactly how much work it is doing and why. Proving that the comet did not contribute to the CME is not the same as proving that it did not. Proving a negative in a complex dynamic system requires a level of counterfactual certainty that the field of solar physics does not yet possess. To demonstrate definitively that the CME was unrelated to the sungrazer passage, you would need to show that the CME would have occurred at that specific time, from that specific region, at that specific intensity, in the absence of the comet. That demonstration requires a predictive model of solar behaviour precise enough to reconstruct what would have happened in an alternative history where the comet was not present. Solar forecasting has improved substantially over the past 2 decades, but it is nowhere near the precision required to support that kind of counterfactual claim with confidence. The honest statement is not that the CME was unrelated to the comet. The honest statement is that the available evidence was insufficient to establish a relationship, and insufficient evidence for a connection is not the same as evidence against one. This distinction matters because it defines the epistemic status of the 2011 event accurately. It is not a confirmed case of comet-corona interaction producing a CME. It is also not a confirmed case of coincidence. It is an unresolved observation, a data point that is consistent with the interaction hypothesis and also consistent with coincidence, in a context where the available instruments and analytical methods could not distinguish between those two interpretations with sufficient confidence to close the question. The event demonstrated the existence of a question rather than providing an answer to it. It showed that the timing of coronal events relative to sungrazer passages can produce apparent correlations that require explanation, even when the explanation ultimately reached is probably coincidental. And it established in the peer-reviewed literature, however contested, a scientific precedent for treating the comet-CME interaction hypothesis as a legitimate subject of investigation rather than a fringe speculation unworthy of serious attention. The specific physical mechanism that would connect a small sungrazer to a large-scale solar eruption has never been fully worked out in a way that satisfies the standards of the field. The proposed pathways involve the comet's ionized debris interacting with existing magnetic field structures in the corona, potentially perturbing field configurations that are already close to reconnection threshold and pushing them across the stability boundary they had not quite reached on their own. The analogy sometimes used is a supersaturated solution, a liquid that is technically at the point of crystallization but has not yet begun to crystallize, requiring only a small perturbation, a dust particle or a vibration, to trigger the process. In this model, the comet does not cause the CME in the sense of providing the energy for it. The Sun provides all the energy. The comet potentially provides the perturbation that releases energy the Sun had already stored. Whether this mechanism operates in practice, under what conditions and at what comet sizes, the effect becomes physically significant. These questions were not answered by the 2011 event and remain open. What has changed between 2011 and 2026 is the quality of the instruments available to observe the answer. The Daniel K. Inouye Solar Telescope, now operating from Haleakala at a spatial resolution that renders features smaller than a city visible on the solar surface, provides a level of magnetic field mapping in the corona that did not exist in 2011. SDO continues to operate with the same multi-wavelength cadence that made it valuable 15 years ago. Additional heliospheric imaging instruments have been added to the monitoring network. The Solar Orbiter mission provides a second viewing angle on solar events that single-point observations cannot replicate. And the object making the April 4th perihelion pass is larger, potentially significantly larger, than the small fragment that generated the 2011 correlation. A larger object deposits more material in the corona. More material means a larger potential interaction signal. A larger signal is more distinguishable from background noise. The 2011 event asked a question and left it open. 2026 has a larger comet, better instruments, and a scientific community that has spent 15 years thinking about what it would need to see to distinguish interaction from coincidence. We may get a definitive answer on April 4th. We may get a more sophisticated version of the same ambiguous result that 2011 produced. Either outcome advances the science, but if it happens again, if a comet passes through the corona and a significant CME follows within hours, the data available to analyse at this time will be categorically better than anything that existed the last time we watched and wondered. This time, whatever the Sun does in response to its visitor, we will not be left wondering whether we had the instruments to see it clearly. We will know, and knowing, even when the answer is complicated, is always better than the alternative. Part 8. Avi Loeb and the Interstellar Question. Avi Loeb is the kind of scientist whose name functions as a warning label in certain academic circles, not because he is incompetent, the opposite problem, if anything. Loeb is a professor of science at Harvard University, former chair of the astronomy department, and the author of hundreds of peer-reviewed papers across cosmology, astrophysics, black hole physics, and the early universe. His publication record is extensive enough, and his institutional standing credible enough that dismissing him requires effort that most critics would prefer not to expend. The friction he generates in the scientific community comes not from a deficit of credentials, but from a surplus of willingness to say things out loud that his colleagues feel should remain unsaid, or at least unpublished, until the evidence supporting them is considerably stronger than it currently is. The event that defined his public profile and permanently altered his relationship with a significant portion of the astronomical community was his response to Oumuamua. When the first confirmed interstellar object was detected passing through the inner solar system in 2017, the anomalies in its behaviour generated a range of proposed explanations from researchers across the field. Oumuamua was not outgassing in the way a comet should. It was accelerating away from the Sun at a rate that exceeded what solar radiation pressure alone could account for. Its shape, inferred from the way its brightness varied as it rotated, suggested something extremely elongated or extremely flat. Nothing like the roughly spherical or irregular shapes typical of known solar system objects. These anomalies were real. The data producing them was not seriously disputed. What was disputed vigorously was what they meant. Most researchers proposed natural explanations. Outgassing of hydrogen, invisible to standard detection methods, could account for the non-gravitational acceleration. An unusual material composition, perhaps a fragment of solid hydrogen ice, or a piece of nitrogen ice sheared from the surface of a Pluto-like body in another star system, could explain both the shape inference and the radiation response. Measurement uncertainties, combined with the difficulty of observing a fast-moving faint object on a short timeline, left room for explanations that required no departure from known physics. The field converged, imperfectly and without full consensus, on natural origin as the working assumption. Loeb published a different hypothesis. He proposed that Oumuamua's anomalous properties were consistent with an artificial origin, specifically with a light sail, a spacecraft propelled by radiation pressure, constructed by an intelligent civilization in another star system. He was careful, in the technical presentation of this hypothesis, to frame it as one possibility among several rather than a conclusion. He noted that the same intellectual honesty that requires considering natural explanations requires considering artificial ones if the data does not definitively exclude them. He argued that the reluctance of the scientific community to engage seriously with the artificial origin hypothesis reflected a cultural conservatism, a preference for uncomfortable natural explanations over even more uncomfortable artificial ones, rather than a genuine empirical argument against it. The response was what you might expect. Some colleagues engaged with the hypothesis seriously and found it insufficiently supported by the available evidence. Others were less measured. The public attention generated by Loeb's position was enormous by the standards of astronomical research, and that attention itself became a source of friction, the perception that he was using an extraordinary claim to generate publicity rather than to advance understanding. Loeb has consistently rejected that characterization and continued to pursue the question through his Galileo project, an initiative specifically designed to apply rigorous scientific methodology to the search for evidence of extraterrestrial technological objects. Whether you find his approach admirable or exasperating depends considerably on your prior beliefs about the appropriate relationship between evidence and hypothesis in scientific practice. Both positions are held by serious people. All of this background matters for understanding why, when Loeb raised a question about C/2026A1 in relation to the interstellar object 3I/8LAS, the response split predictably along already established lines. Some people took the question seriously because Loeb has a track record of identifying anomalies worth examining. Others dismissed it reflexively because his name had become, in certain contexts, a signal for overreach rather than insight. Neither response engaged fully with what Loeb actually said, which was more careful and more interesting than either reaction acknowledged. 3I/Atlas is the third confirmed interstellar object detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. It was detected in 2025 and, like its predecessors, is travelling on a hyperbolic trajectory that will carry it back out of the solar system and into interstellar space on a timescale of years. It arrived with its own set of anomalous characteristics. Brightness inconsistent with size, estimates derived from its discovery photometry, trajectory details that generate competing interpretations, and it has produced its own subset of researchers, paying close attention to details that do not resolve cleanly under standard models. It is, in other words, precisely the kind of object that Loeb's analytical framework is designed to engage with. Loeb's question about the relationship between 3I/Atlas and C/2026A1 was essentially this. Given the temporal proximity of an interstellar object passing through the solar system and a Kreutz sungrazer arriving at perihelion, is there any physically plausible mechanism connecting them? Could the gravitational influence of the interstellar object have perturbed the comet's orbit in ways that affected its current trajectory? Could there be some deeper dynamical relationship between the two events that the coincidence of timing hints at? His own answer, arrived at through the kind of back-of-envelope calculation that experienced astrophysicists perform before committing to more elaborate analysis, was no. The size discrepancy between the two objects is too large for meaningful gravitational interaction at the distances involved. The orbital inclinations differ enough that the geometry of any close approach between them, at any point in their respective histories, does not support the hypothesis of significant gravitational perturbation. The timing coincidence, while cosmetically striking, does not survive quantitative scrutiny as evidence of a causal relationship. Loeb raised the question, applied the relevant physics, found the answer unsatisfying in the direction of connection and said so. That process, ask the uncomfortable question, do the calculation, accept the result regardless of its narrative appeal, is exactly what the scientific method is supposed to look like. The fact that the question generated attention disproportionate to its final answer is a feature of the media environment around Loeb's name, not a feature of the question itself. But the act of raising the question, even in the process of dismissing it, points towards something genuine and worth examining carefully. The classification systems we use for solar system objects, comets, asteroids, Kreutz sungrazers, Oort cloud objects, interstellar visitors, were constructed from decades of observation using instruments that could only detect the brightest, largest, and most conveniently positioned objects in each category. The existence of these categories feels stable and complete from inside the current observational framework. It felt equally stable and complete before the detection of Oumuamua demonstrated that an entire category of objects, interstellar transients, had been missing from the inventory entirely, not because they did not exist, but because the instruments needed to detect them had not yet been built. That precedent is uncomfortable in ways that extend beyond the interstellar object category specifically. If an entire class of solar system visitors was absent from our models until 2017, what else might be absent? Not as conspiracy or as dramatic revelation, but as the ordinary and expected consequence of building a scientific understanding from an observational sample that covers only a few decades of a system that has been operating for 4.5 billion years. The events we have witnessed represent a fraction so small of the total history of solar system dynamics that describing our current models as complete would require a confidence in extrapolation that the history of science consistently fails to reward. C/2026 A1 is almost certainly not an interstellar object. Its orbital characteristics, while anomalous within the Kreutz family classification, trace back to a solar system origin through lines of evidence that are considerably stronger than anything supporting an interstellar hypothesis. The connection Loeb explored was probably not real, and his own analysis confirmed that, but the broader habit of thought that the exploration represents, the willingness to ask whether the categories we use are adequate to the phenomena we observe, whether our confidence in our classifications is proportional to the evidence supporting them, whether the boundaries we have drawn around our understanding are boundaries of knowledge or boundaries of instrumentation, that habit of thought is not only legitimate but necessary. The questions that feel impolite to ask in science are often precisely the questions most worth pursuing, not because impolite questions are more likely to be correct, they are not, but because the discomfort they generate in established frameworks is sometimes a diagnostic signal, a sign that the framework has an edge. It is not fully examined, a category boundary drawn by the limits of observation rather than by the limits of nature. Loeb asks those questions more publicly and more persistently than most of his colleagues prefer. Whether that is a virtue or a flaw depends on whether the questions turn out to point somewhere real. In the case of interstellar objects, the most uncomfortable question of 2017 turned out to point toward a category that genuinely existed and genuinely mattered. In the case of C/2026 A1 and 3I/Atlas, the question pointed nowhere physically significant. Both outcomes are informative, and neither one suggests that the questioning should stop. Part 9. The Kreutz lineage problem. 2,000 years ago, something catastrophic happened in the outer solar system that most people have never heard of. Not a collision, not an explosion in any conventional sense. Something quieter and, in its own way, more consequential. A massive comet, potentially one of the largest that has ever passed through the inner solar system in the period of human civilization, came too close to the Sun and did not survive the encounter intact. Instead of passing by as a single object and continuing on its orbit, it fragmented. The gravitational and thermal forces at close solar approach overwhelmed whatever structural integrity held the nucleus together, and the object broke. Not into two pieces, not into a handful of identifiable chunks, into a cascade of fragments ranging from boulder-sized debris to objects several kilometers across, each inheriting a slightly different version of the original orbit, each beginning its own independent journey through the solar system. The pieces did not all fall into the Sun simultaneously. They dispersed along slightly varied trajectories, some falling back in on a schedule close to the original orbital period, others drifting into variations that would carry them back on longer or shorter timescales. Some arrived at the Sun within decades of the original fragmentation. Others were deflected into orbits that would take centuries, and some, the ones on the longest inherited trajectories, would not return for millennia. The descendants of that ancient comet have been arriving at the Sun ever since, one after another, across centuries and millennia, each one a fragment of something that no longer exists as a unified object. We call them the Kreutz sungrazers, and the comet racing toward perihelion on April 4th is almost certainly one of them. The Kreutz family is identified by a shared set of orbital characteristics: the inclination of the orbit relative to the plane of the solar system, the direction of the orbital plane in space, and the perihelion distance, the point of closest approach to the Sun. These parameters trace back to the original fragmentation event and are distinctive enough that new sungrazers can be identified as Kreutz family members before they ever reach the Sun, purely from the geometry of their approach. The family has a signature. Every member carries it. The Solar and Heliospheric Observatory, SOHO, has catalogued over 3,000 Kreutz sungrazers since it began operation in 1995, the vast majority of them tiny fragments invisible from Earth that SOHO's coronagraph detected only because it blocks out the Sun's disk to observe the surrounding space. 3,000 objects, all descended from one catastrophic moment, all converging on the same star across the span of recorded human history and well beyond it. Within the Kreutz family, astronomers recognize several subgroups based on refined orbital parameters. These subgroups represent distinct fragmentation lineages, moments in the ancient breakup sequence when particular pieces separated and began their own orbital evolution. Think of it as a family tree with multiple branches, each branch representing a different generation of fragmentation. The first breakup produced the primary lineages. Later, close solar passes by the surviving large fragments produced secondary breakups. Those secondary fragments, on their own orbital schedules, produced tertiary ones. The result is a nested family structure where the orbital parameters of any given sungrazer encode information about when and how its particular ancestral fragment separated from the main body. Knowing which subgroup a comet belongs to tells you something meaningful about its likely composition, its structural characteristics, and its probable behavior near the Sun. It situates the object within the family tree of that ancient catastrophe, and by extension, it gives you a basis for predicting how it will behave when it returns to the environment that destroyed its ancestor. Subgroup membership is, in a practical sense, a survival profile. Objects from certain lineages tend to fragment earlier in their approach. Objects from others tend to be more structurally coherent. The classification is not just academic, it is predictive. C/2026A1 does not sit cleanly in the family tree. Its orbital period of approximately 1900 years, its specific inclination and perihelion approach parameters, they are Kreutz-like, recognizably related to the family signature, but they do not match the documented subgroups with the precision you would expect if this object were a well-understood lineage member. It is close enough to belong to the family. It is different enough that nobody can say with confidence which branch of the family it comes from. Several researchers have noted this discrepancy and raised the possibility that C/2026A1 represents a previously uncharacterized subgroup, a fragmentation branch that separated at a different time or under different conditions than the known lineages, producing a line of descendants that we have not previously identified or studied. This matters more than it might initially appear to. If this object comes from an uncharacterized branch of the Kreutz family, it means the fragmentation history of the ancestral comet is not yet fully mapped. We have been watching the Kreutz family for decades. We have catalogued thousands of its members. We have published detailed analyses of the known subgroups and constructed models of how the original fragmentation event unfolded, and we may still be missing entire chapters of the story. A 2,000-year orbital period means that some family members have not returned to the inner solar system since before the telescope was invented, before the scientific method was formalized, before modern astronomy existed as a discipline. We have been building our understanding of this family from an attendance record that is, by necessity, incomplete. The members on the longest orbits simply have not shown up yet during the period when we are capable of recording their arrival. There is also a broader implication that extends beyond the Kreutz family specifically. This family represents our most detailed case study in cometary fragmentation, the process by which a large solar system body breaks into smaller pieces over time, each piece eventually returning to the inner solar system on its own schedule, each carrying information about the composition and structure of the original object. This process is not unique to the Kreutz family. It happens across the solar system, producing families of asteroids, meteor streams, and comet groups whose relationships to each other are still being mapped. The Jupiter family comets, the Halley-type comets, the various identified asteroid families in the main belt. All of these represent the products of fragmentation events at different times and scales. Every time we discover a Kreutz sungrazer that does not fit the existing classification system, we are adding a data point to a puzzle whose full dimensions we do not yet know. We are demonstrating that the fragmentation history of the solar system is more complex than our current models accommodate. The compositional uncertainty created by C/2026 A1's ambiguous subgroup membership is directly relevant to what happens on April 4th. The ratio of ice to rock in a cometary nucleus determines how it responds to solar heating. A nucleus with high volatile content will begin outgassing earlier and more violently, potentially destabilizing its own structure through jet activity before it even reaches the corona. A nucleus with lower volatile content and higher rock fraction will resist thermal disruption longer, but may be more susceptible to tidal forces near perihelion. The structural porosity of the nucleus, how loosely or tightly the material is packed, affects how tidal forces propagate through the body. All of these properties vary across different cometary lineages, and without knowing which lineage C/2026 A1 belongs to, our predictions about its behavior carry a larger uncertainty margin than we would like. What we can say is this. The last time this particular object was in the inner solar system, nobody was watching with instruments. Nobody had a telescope. Nobody had a coronagraph or a space-based observatory, or a magnetometer network or a real-time data feed from a satellite in solar orbit. Nobody wrote down what they saw in a form we have been able to connect to this specific object, though they may have seen something. There may be ancient accounts somewhere in the historical record, texts describing an unusual brightness near the sun, a daytime apparition, a tail visible against the sky at dusk or dawn, that correspond to C/2026A, one's previous perihelion past 1900 years ago. Ancient Chinese astronomical records, Roman natural histories, Greek observational texts, these sources contain descriptions of unusual celestial events that have never been fully cross-referenced against the orbital histories of known Kreutz sungrazers. The work of connecting those ancient descriptions to specific objects is painstaking, incomplete, and ongoing. We may be looking at a missing chapter in a 2,000-year-old story, a chapter that was written once in observation and in awe by people who had no framework to understand what they were seeing, and that is now about to be written again, this time with the full apparatus of modern solar science pointed directly at the moment of its arrival. The object that was a mystery to everyone who saw it last time will not be a mystery to the instruments watching it this time. Whatever it is, wherever exactly it comes from within the Kreutz lineage, whatever structural secrets it has been carrying through the darkness for 19 centuries, April 4th is when it gives them up. We are finally equipped to read the chapter. The only question is what it says. Part 10. The Carrington Layer. On September 1st, 1859, a British astronomer named Richard Carrington was observing sunspots through his telescope when he witnessed something that had no name yet. He was not looking for anything unusual. Sunspot observation was routine scientific work in 1859, careful, methodical, the kind of work that fills notebooks with careful sketches and precise measurements without producing much drama. Carrington was good at it. He had been doing it for years. And then, without warning, a brief and intensely brilliant flash of white light erupted from a sunspot region on the solar surface, visible in ordinary white light through an ordinary telescope without any specialized equipment or filters beyond what Carrington already had in place. He watched it for several minutes. He called a colleague to confirm what he was seeing, and then it faded, and the sun looked normal again, and Carrington had no framework to fully understand what he had just observed. Within hours, the world informed him. Telegraph systems across North America and Europe began to malfunction in ways that operators had never encountered. Some reported receiving electrical shocks directly through their equipment. Others discovered that their lines were actively transmitting messages even when completely disconnected from their power sources. The geomagnetically induced currents flowing through the telegraph wires were strong enough to operate the equipment on their own. Sparks flew from telegraph machines. Paper caught fire. Operators disconnected their batteries entirely and continued to send and receive messages using only the current the Earth itself was providing. The following night, auroras appeared as far south as Cuba, Colombia, and Hawaii. People across the tropics woke in the middle of the night convinced that the nearest city was burning. The light was that bright, that red, that wrong. What Carrington had witnessed was a solar flare of extraordinary magnitude, the largest ever recorded in the observational period, followed almost immediately by a coronal mass ejection of equally extraordinary intensity. The CME transited from the Sun to Earth in approximately 17 hours. Typical CMEs take between 1 and 3 days. This one moved so fast that it outran the usual precursor signals that might have provided warning. The geomagnetic storm it produced upon arrival is the most intense ever documented. We call it the Carrington event. And for the past several decades, a quiet but persistent community of solar physicists, infrastructure engineers, national security analysts and emergency management planners has been sitting with one deeply uncomfortable question. What happens when it happens again? Because it will happen again. This is not speculation. This is statistics applied to a physical process that has been operating for 4.5 billion years. The Sun produces extreme flares. The historical record, reconstructed from ice cores that preserve the chemical signature of intense solar particle events, shows that events at or beyond Carrington intensity have occurred multiple times in the last few thousand years alone. The Carrington event is not an outlier in the geological sense. It is a rare but recurring feature of our star's behaviour, the kind of event that appears perhaps once or twice per century at full intensity, with lesser versions appearing more frequently. The question is not whether it will recur. The question is whether we will be ready when it does. The world of 1859 was electrically simple, in a way that is almost impossible to fully appreciate from the vantage point of 2026. The telegraph was the most sophisticated electrical technology in widespread use. It was vulnerable, and it failed dramatically, but the failure was recoverable. No telegraph line took months to repair. No component of the telegraph network required custom manufacturing at a lead time of a year or more. Operators cleared the sparks, replaced the damaged equipment, and the system was functional again within days. The disruption was dramatic and memorable, and completely survivable at a civilizational scale. The world of 2026 is not electrically simple. It is the opposite of electrically simple. We have constructed, over the past century and a half, a global infrastructure of staggering complexity and almost total dependence on continuous, stable electrical supply. Consider what actually runs on electricity in the modern world, not just the obvious things like lights and appliances, but the things whose electrical dependence we rarely think about. Water treatment and distribution systems run on electric pumps. Food supply chains depend on electrically powered refrigeration at every stage from farm to table. Financial systems process transactions through data centers that require uninterrupted power to maintain the integrity of records. Hospitals run life-sustaining equipment on electrical systems backed by generators that themselves depend on fuel supply chains. Communications infrastructure, cellular networks, internet routing, satellite uplinks operates on electrical power with backup systems designed for outages measured in hours, not weeks. Layered on top of all of this is the satellite network. We have placed hundreds of operational satellites in low Earth orbit that are essential for GPS navigation, weather forecasting, financial transaction timing, military communications, and an expanding range of commercial services. These satellites operate in the environment most directly exposed to geomagnetic storms. A Carrington-level event would expose them to radiation and particle fluxes far beyond their design tolerances. Significant portions of the operational satellite fleet could be damaged or rendered non-functional within the first hours of such an event. GPS degradation alone, even partial, even temporary, would affect aviation, maritime navigation, precision agriculture, emergency response coordination, and the timing signals that synchronize financial networks. And then there are the transformers. High-voltage transformers are the critical nodes of continental power grids, the large heavy components that step voltage up and down at transmission and distribution points. They are not interchangeable. They are custom-built for specific grid locations. They are not manufactured in large quantities and warehoused for rapid replacement. Lead times for a large power transformer, from order to delivery, can run from 1 to 3 years under normal manufacturing conditions. The geomagnetically induced currents that a Carrington-level storm would drive through power grid conductors are capable of overheating and permanently damaging these components. The 1989 geomagnetic storm, which reached an intensity of roughly 1% of Carrington-level estimates, collapsed the entire Hydro-Quebec power grid in Canada in 90 seconds and left 6 million people without electricity for 9 hours. A true Carrington repeat, hitting a modern continental grid, could produce transformer damage on a scale that makes 9 hours look like a rounding error. Some assessments have suggested potential outage durations measured in months, affecting regions rather than provinces, with cascading failures propagating through the interconnected grid in ways that are difficult to model and harder to stop. This is the real risk at the centre of the space weather conversation, and it is important to state clearly, it exists completely independently of any comet, C/2026. A1 did not create this vulnerability. It will not resolve it. The Sun was capable of producing a Carrington-level event before the comet entered the inner solar system, and it will remain capable of producing one long after April 4th has come and gone. Solar cycle 25 has already generated significant flares from active sunspot regions that require no outside influence to produce CME-level eruptions. The risk was real before anyone had heard this comet's designation. It will be real after perihelion regardless of whether the comet survives or disintegrates in the corona. Where the comet becomes genuinely relevant to this conversation is in something less physical and more human, the domain of attention. We are not, as a civilization, particularly good at preparing for low-frequency, high-consequence events. We tend to prepare for the threats that are immediately visible, recently experienced, or narratively compelling. Geomagnetic risk has been documented, assessed, and reported on for decades. The scientific literature is extensive. The engineering solutions, grid hardening, transformer protection, satellite shielding protocols are known and in many cases technically feasible. What has been lacking consistently is the public and political attention required to fund and implement those solutions at the necessary scale. When a sungrazing comet arrives during solar maximum, while triple CMEs are already striking Earth, while a fireball is falling over Ohio, and a Harvard professor is raising questions about interstellar connections, the attention paid to space weather intensifies dramatically. Media coverage increases, social media engagement increases, the number of people who learn for the first time that the Sun is capable of doing serious damage to the infrastructure they depend on every day increases. That attention is not misplaced. It is just aimed at a slightly imprecise target. The comet is not the threat. The comet is the spotlight that illuminates the threat that was already there. The Carrington event was not caused by a comet. The Quebec blackout of 1989 was not caused by a comet. The satellites that will be affected in the next serious geomagnetic storm will not be affected because an ancient sungrazer triggered the eruption. The source of the risk is the star at the centre of our solar system, operating exactly as it has always operated, producing exactly the events that its physics has always produced. The danger is not what is travelling toward us from the darkness. The danger is what we have built underneath a star we have always treated as background, stable, permanent and safe, and our collective, persistent, expensive reluctance to take seriously the evidence that none of those assumptions are guaranteed. The Sun has been doing this for 4.5 billion years. We have been building electrical civilization for about 150 of them. The math on that gap is not comfortable, but it is honest, and honest is where any real preparation has to start. Part 11. The other comet. Everyone is ignoring. While every telescope and every curious person on the internet is watching C/2026A, one fall toward the Sun, another comet is quietly brightening in the evening sky, and almost nobody is talking about it. That oversight is understandable. When one story involves a potential daylight comet, a solar corona interaction, a Harvard professor raising interstellar questions, and a perihelion date circled in red on every space weather calendar in the world, the competing story about a perfectly ordinary comet following a perfectly ordinary orbit tends to get lost. But C/2025 R3 Pan-STARRS deserves better than that. And the reasons it deserves better tell us something interesting about how we pay attention to the sky, and what we miss when we only look at the loudest thing in the room. C/2025 R3 Pan-STARRS is not a sungrazer. Its perihelion distance, its point of closest approach to the Sun, places it comfortably beyond the dangerous zone that defines the sungrazer category. It will not enter the corona. It will not experience the thermal vaporization and tidal forces that are about to subject C/2026A1 to the most extreme environment in the local solar system. It will not interact with solar magnetic fields in ways that produce plasma disturbances or raise questions about CME triggering. It will not be watched by solar physicists with quiet professional anxiety. It will simply be a comet, doing what comets do when the solar system treats them with basic decency, outgassing steadily as it approaches the sun, developing a coma, growing a tail, brightening gradually and predictably, and becoming visible to anyone who knows where to look, and it may become quite visible. Current brightness estimates for C/2025 R3, pan stars around its perihelion period, place it at approximately magnitude 2. For non-specialists, the magnitude scale in astronomy runs counterintuitively. Lower numbers mean brighter objects, and the scale is logarithmic, meaning each step represents a significant difference in actual brightness. Magnitude 2 places this comet in the same general brightness range as some of the more prominent stars in the night sky. Polaris, the North Star, sits at approximately magnitude 2. The stars of the Big Dipper range from about magnitude 2 to 3. A comet at magnitude 2, under reasonably dark skies away from significant light pollution, is unambiguously visible to the naked eye without any optical aid whatsoever. You do not need a telescope. You do not need binoculars. You need to know where to look and to be somewhere dark enough to see it. The geometry of the observation window for C/2025 R3 from the Northern Hemisphere is relatively favourable during its peak brightness period. This matters more than casual observers typically realise. A comet's brightness as seen from Earth is only part of the equation. Its angular separation from the Sun determines whether it is observable at all. A bright comet sitting too close to the Sun in the sky is effectively invisible, drowned out by solar glare regardless of its intrinsic luminosity. C/2025 R3's orbital geometry during perihelion places it at a separation from the Sun that allows for observation in the evening sky after sunset, when the sky is dark enough to see it but the comet is still above the horizon. That combination, brightness plus favourable geometry plus Northern Hemisphere visibility, is rarer than it sounds. Many comets that reach naked eye brightness do so under conditions that make them difficult or impossible to observe for most of the world's population. This one appears to be an exception. In an ordinary year, C/2025, R3 pan stars would be the main event of the astronomical calendar for the first half of 2026. It would be the comet that astronomy clubs organised observation nights around, booking dark sky sites months in advance. It would be the subject of articles in popular science publications advising readers on optimal viewing times, recommended optical equipment, and the best geographical locations for unobstructed views of the western horizon after sunset. Amateur astrophotographers would be planning their equipment loadouts and scouting locations with interesting foreground elements: mountains, old buildings, bodies of water that could provide reflections of the tail. The projected peak brightness, the expected tail length, the observational window, all of these things that normally constitute the complete conversation about a noteworthy comet, are present for C/2025 R3, fully intact, waiting for attention that is currently going elsewhere. This is itself a phenomenon worth examining because it says something true about how human attention operates in an information-saturated environment. We have a finite capacity for wonder, or at least a finite capacity for focused wonder, directed at any particular category of thing at any given moment. When two stories compete for the same attentional space, one dramatic and uncertain and potentially alarming, the other beautiful and predictable and rewarding, the dramatic story wins almost every time. The comet that might trigger a solar eruption is simply a more compelling narrative object than the comet that will quietly light up the evening sky and then move on. This is not a flaw in human cognition. It is a feature. Attention evolved to track threats and novel events, not to distribute itself equitably across all available objects of interest. But it produces a real observational cost, which is that the quieter, more accessible, more reliably rewarding story gets buried. C/2025 R3 will develop its tail whether anyone is watching or not. It will peak in brightness on its own schedule, indifferent to the competition. It will cross the evening sky over April and into May, offering anyone who looks up on a clear night a view of something genuinely ancient and beautiful, a visitor from the outer solar system carrying ice and dust and organic compounds that formed at the same time as the Earth itself, briefly close enough to be seen with unaided human eyes before retreating back into the cold. That is not a minor thing. That is exactly the kind of event that reminds people why astronomy exists as a human practice, not just as a professional discipline pursued in observatories and published in journals, but as a direct, unmediated encounter between a person standing on a planet and the universe that surrounds them. The contrast between these two April comets is, when you sit with it, almost philosophically instructive. C/2026 A1 arrives from an ancient catastrophe on a trajectory that amounts to a physics experiment conducted at the most extreme scales available in the inner solar system. Its outcome is genuinely unknown. It may survive and produce a spectacular display. It may fragment and die in the corona. It may do something in between that raises more questions than it answers. The entire encounter, from corona entry to perihelion and beyond, will last a matter of hours. Blink and you miss it, if you are even equipped to see it at all, given that the most dramatic phases occur in the immediate vicinity of the Sun rather than in the observable night sky. C/2025 R3 asks nothing dramatic of anyone. It approaches, brightens, develops a tail that may extend several degrees across the sky, reaches peak visibility over a window of days rather than hours, and then gradually fades as it moves back toward the outer solar system. It rewards patience and planning. It is observable with the naked eye from a suburban backyard on a clear night. It does not require solar telescopes or real-time data feeds, or a background in plasma physics to appreciate. It is accessible in a way that the sungrazer simply is not, and that accessibility is a genuine gift at a moment when most of the space weather conversation is pitched at a level of complexity and anxiety that leaves casual observers feeling more alarmed than informed. What April of 2026 represents, for anyone paying attention to both stories simultaneously, is something that does not happen often. Two comets, both active, both observable in some form, both offering something real, one a scientific event of potentially significant consequence, the other a quiet and reliable visual reward, occupying the same sky at the same moment in time. The solar system rarely schedules its events with this kind of accidental variety. Usually the dramatic things happen in isolation, separated by the long, empty intervals that characterize most of astronomical time. April 2026 compresses two different kinds of comet story into the same calendar month, and the fact that one of them is being almost entirely ignored in favor of the other is a choice we are making, not a necessity imposed on us. The sky in April 2026 is, by any reasonable measure, worth looking up at. Both of them are up there. One of them might change what we know about the Sun, the other one will simply be beautiful. And on reflection, there is no good reason to choose between them. Part 12. The crowded sky problem. In 1 week earlier this month, 18 separate asteroid close approaches to Earth were logged in official tracking databases. 18 in 7 days. Take a moment with that number because it does not match most people's intuitive picture of the space surrounding our planet. The popular imagination of space is largely empty, vast, dark, and quiet, with objects separated by distances so enormous that encounters between them are vanishingly rare. That picture is not wrong at the scale of the galaxy, or even the solar system as a whole. But in the specific neighbourhood our planet occupies, the slice of space within a few million kilometres of Earth's orbital path, the reality is considerably more populated than the intuition suggests. And the question of how we interpret that population, what it means, what it implies, and what it should make us do differently, is one that planetary defence researchers have been working on quietly for decades, while the rest of the world focused on other things. The number 18 is either reassuring or alarming, and which one it is depends almost entirely on the interpretive frame you bring to it. The reassuring interpretation runs like this. Those 18 objects were detected, tracked, assessed, and confirmed as non-threatening before they made their closest approaches. The systems designed to find near-Earth objects found them. The orbital calculations were performed, the impact probabilities were computed and found to be negligible. The whole apparatus of planetary defence observation worked exactly as intended, and the result was 18 non-events that most people never heard about because there was nothing to report. That is a success story. That is the system functioning correctly. The alarming interpretation runs like this. 18 objects passed within catalogued close approach distance of Earth in a single week, and every one of them was found by survey instruments that cover only a fraction of the relevant sky. at sensitivity thresholds that render certain categories of objects effectively invisible during a period when at least one known observational blind spot, the direction of the Sun, remains largely unmonitored by ground-based optical systems. If 18 were found, how many were not found? That is not a rhetorical question. It is a genuine, open, technically important question that the planetary science community takes seriously and the general public almost never thinks about. Detection systems for near-Earth objects have improved dramatically over the past 2 decades, and that improvement is real and significant and worth acknowledging. Survey programs like the Catalina Sky Survey, operating from telescopes in Arizona and Australia, scan large sections of the sky on a repeating cadence, comparing successive images to identify objects that move against the background of fixed stars. The Pan-STAR system in Hawaii does the same across a different portion of the sky. The Atlas Survey, also operating from Hawaii with additional stations added in recent years, specializes in detecting objects on short warning timescales, things that are already close and moving fast. Between these programs and several others, the catalogued population of near-Earth objects now numbers in the hundreds of thousands, and new discoveries are added at a rate of several thousand per year. The database is genuinely large, genuinely comprehensive for objects above certain size thresholds, and genuinely useful for assessing impact risk over meaningful timescales. But the database of known objects is not the complete population of existing objects. This distinction is important and is sometimes lost in public discussions of planetary defense. When agencies report on near-Earth object surveys, they report on the known population, the objects that have been detected, tracked for long enough to establish reliable orbits, and added to the catalogue. The completeness of that catalogue depends on the size of the objects in question. For large objects, those above roughly 1 kilometre in diameter, the scale at which an impact would produce regional to global catastrophic effects, surveys are estimated to have found approximately 95% of the population. That is a genuinely impressive achievement, and it means that the risk of an undetected large impactor arriving without warning is very low. For smaller objects, the completeness drops dramatically. Objects in the 20 to 140 metre range, the scale relevant to city-destroying or regional damage events, the scale of the Tunguska impactor in 1908, and well above the scale of the Chelyabinsk meteor, are estimated to be catalogued at somewhere between 40 and 50% completion at best. More than half of the objects in this size range that cross Earth's orbital path have not yet been found. They are out there. They are moving. We simply do not know where they are because we have not looked in the right place at the right time with sufficient sensitivity to detect them. Detection efficiency is not uniform across the sky, and the gaps are not random. They are structural. Small dark objects, those with low reflectivity surfaces that absorb rather than reflect light, are harder to detect at any given distance than brighter objects of the same size. Objects approaching from the general direction of the Sun are effectively invisible to ground-based optical surveys, because pointing a telescope toward the Sun during daylight is not useful, and the region of sky near the Sun remains in the daytime sky for extended periods. This is not a minor blind spot. A significant fraction of all possible Earth-approaching trajectories include an approach geometry that keeps the object in the solar direction until it is very close. The Chelyabinsk meteor of 2013 arrived from exactly this direction. It was approximately 20 meters across, well above the threshold for cataloguing at high completeness, and no survey detected it before it entered the atmosphere. The airburst it produced when it disintegrated at high altitude released energy equivalent to approximately 500 kilotons of TNT. To put that in terms that are easier to hold in the mind, that is roughly 30 times the energy of the nuclear weapon dropped on Hiroshima. Approximately 1,500 people were injured, nearly all of them by glass shattered by the pressure wave that travelled outward from the detonation point in the upper atmosphere. Windows failed across an area of thousands of square kilometres. Buildings were structurally damaged, and the object that caused all of this had been moving through the solar system for the same amount of time as everything else. We simply had not found it, because it came from the one direction we could not easily watch. The Ohio fireball from March 17th of this year sits at the smaller end of this same spectrum, an estimated 7 tons of material entering the atmosphere without prior detection, producing a visible and audible event across multiple states. The energy release, approximately 0.37 kilotons, is not in the same category as Chelyabinsk. It is not a regional threat. It did not injure anyone or damage infrastructure, but it is a data point in the same argument. because it represents an object that was in the solar system, on an Earth-crossing trajectory, until the moment it ceased to exist as a solid object in our upper atmosphere, and nobody knew it was there before it arrived. At 7 tons, that is essentially guaranteed, objects of that mass are simply too small and too numerous to catalogue individually. But the principle scales upward in ways that are less comfortable. The apparent increase in log detection events over the past decade is not evidence that the solar system is becoming more crowded. The solar system's object population is not meaningfully changing on human timescales. What is changing is our ability to see it. Better instruments, wider survey coverage, faster data processing, and more survey programs operating simultaneously have produced a detection rate that is higher than it has ever been. We are seeing more because we are looking harder and looking better, and that is genuinely good news. An object you know about is an object you can potentially do something about, at sufficient warning time. But seeing more does not mean seeing everything, and the gap between those two things is where the honest risk assessment lives. The objects catalogued in official databases are the ones that existing instruments, pointed in their current directions, operating at their current sensitivity thresholds, happen to find during the period of observation. The ones not in the database are not absent from the solar system, they are absent from the catalogue. That distinction is quiet and technical and does not make headlines. But it is the most important thing to understand about planetary defence as it actually stands today, in 2026. With all of the progress that has been made and all of the progress that remains to be made, in a week where 18 asteroid approaches were logged, solar storms were striking Earth, a sungrazer was closing on perihelion, and a fireball was falling over Ohio, the gap between what we can see and what exists felt unusually present. Not because anything catastrophic happened, nothing catastrophic happened, but because the sequence of events assembled, briefly and without ceremony, a kind of accidental illustration of the environment our planet actually occupies, active, populated, dynamic, and only partially mapped. The solar system is not trying to tell us something. It does not work that way. But if it were, the message would be straightforward. You're not living in empty space. You never were. You're only now beginning to see how full it actually is. Part 13. Interstellar objects are becoming routine. Oumuamua was supposed to be unprecedented, a one-time event. The kind of detection that gets a name and a press conference and a place in the history of astronomy, and then, by definition, never happens again. That is not what happened. When the Pan-STARRS Survey Telescope in Hawaii detected an object in October of 2017 moving through the inner solar system on a trajectory that could not have originated within it, the initial response from the astronomical community was a mixture of excitement and careful disbelief. The mathematics were unambiguous. The object's velocity relative to the Sun and the precise shape of its trajectory indicated a hyperbolic orbit, meaning it was not gravitationally bound to our solar system and had arrived from interstellar space. This had never been confirmed before. Objects from other star systems had been theorized to pass through the solar system, but none had ever been detected in the act. Oumuamua, as it was named, was the first. The scramble to observe it before it left the inner solar system produced some of the most intense short-timeline astronomical observation in recent history. Every available telescope that could be pointed at it was pointed at it. The data collected was real and substantial, and then the interpretations began, and the agreement ended. Oumuamua was elongated, possibly cigar-shaped or pancake-shaped depending on the model, in a way that no known solar system object resembled. It showed no detectable coma or tail, which meant it was not outgassing volatiles the way a comet would. But it was accelerating away from the Sun at a rate that exceeded what solar gravity and radiation pressure alone could account for, and without outgassing. The standard explanation for non-gravitational acceleration in cometary objects did not apply. Theories multiplied in the way theories do when the data is real and the explanation is missing. Cometary outgassing from hydrogen, invisible to standard detection methods. A fragment of exotic material with unusual radiation pressure response. A natural object shaped by extreme tidal forces during a close stellar approach at some point in its past. And then, from Harvard astrophysicist Avi Loeb, a hypothesis that generated a quantity of media attention, roughly proportional to its departure from scientific consensus, that Oumuamua might be an artifact of extraterrestrial technology, a light sail or probe of artificial origin its anomalous acceleration explained by design rather than by natural physics. Most of the field responded with skepticism ranging from polite to emphatic. The debate was vigorous, occasionally pointed, and ultimately unresolved. Oumuamua left the solar system in 2018 and has not been observable since. The question of what it actually was remains technically open. Then, in 2019, Borisov arrived, and the story changed in a direction nobody had quite anticipated. Where Oumuamua had been strange, anomalous, resistant to easy classification, a puzzle that generated more questions than answers, Borisov was almost aggressively ordinary. It had a visible coma, it had a tail. Its outgassing behaviour was consistent with standard cometry models. Spectroscopic analysis of its composition revealed materials recognisable from solar system comets: water ice, carbon monoxide, dust in familiar proportions. By essentially every measure available, Borisov was a comet. It was simply a comet that had come from another star system and happened to be passing through ours on a trajectory that brought it close enough to observe in detail. Its ordinariness, paradoxically, was the most extraordinary thing about it, because if an interstellar comet could be this unremarkable, this consistent with what we already knew about comets in general, it implied that comets from other star systems are not fundamentally exotic objects. They are products of the same basic physics and chemistry that operates in our own solar system, because that physics and chemistry operates everywhere stars form and planetary systems develop. Borisov suggested that interstellar space is not a sterile void between isolated stellar environments, but something more like a continuous medium through which material flows, escaping from one system and occasionally finding its way into another. 3 I/Atlas, detected in 2025, is the third confirmed interstellar visitor and the one most directly relevant to the current moment. It arrived with its own profile of unusual characteristics: brightness inconsistent with standard size estimates, trajectory details that do not fully resolve under conventional cometry models, and a set of competing interpretations that will sound familiar to anyone who followed the Oumuamua story. By the time 3 I/Atlas was detected, the existence of interstellar objects transiting through the solar system was no longer surprising in principle. The category existed. The detection protocols existed. The debate framework existed. What remained surprising, as it does in each individual case, was the specific details that refused to fit cleanly into the established understanding. It is worth pausing on the detection timeline here, because the acceleration from one confirmed interstellar object to 3 in less than a decade is not primarily a statement about how many interstellar objects are passing through the solar system. It is a statement about how much better we have become at finding them. The survey instruments operating in 2017 were already significantly more capable than anything available a decade earlier. The instruments operating now are better still, and the instrument that is expected to transform interstellar object detection most dramatically has not yet reached full operational capacity. The Vera C. Rubin Observatory in Chile, formerly known during its construction phase as the Large Synoptic Survey Telescope, is designed to survey the entire accessible sky every few nights, generating a continuous stream of data identifying objects that move, change brightness, or appear where nothing was previously detected. The scale of its data production is difficult to convey in intuitive terms. Previous surveys identified transient objects in numbers that could be processed and followed up on a manageable schedule. The Rubin Observatory will identify them in numbers that require automated systems to sort and prioritize before human researchers ever see them. The projected discovery rate for interstellar objects, once the observatory reaches full operation, is expected to increase by an order of magnitude or more compared to current rates. We will not suddenly be living in a solar system that receives more interstellar visitors than it does today. We will simply become capable of seeing the ones that were always passing through, invisibly and unrecorded during all the centuries when we lacked the instruments to detect them. The implications of this observational shift for how we understand the solar system's relationship to its surroundings are genuinely significant. The model that positioned our solar system as a largely isolated environment, its contents formed here, evolved here, and fundamentally distinct from whatever exists between the stars, is being replaced by something more porous and more dynamic. The solar system is not an island. It is a node in a network of material exchange that operates across the galaxy at very low densities but over very long timescales. Objects ejected from other star systems during the chaotic early phases of planetary formation or through gravitational interactions in mature systems, travel through interstellar space for millions or billions of years before occasionally intersecting with another system's gravitational influence. Some of those objects pass through without being significantly affected. Some are captured. Some, like Oumuamua and Borisov, and 3 I/Atlas, pass close enough to a star during transit to be briefly observable before continuing on their journeys. This means that the comets and asteroids we think of as native to our solar system, objects formed from the same protoplanetary disk that produced the Earth and the other planets, may have interstellar cousins passing through the neighbourhood right now that we have not yet detected. It means that the compositional record of our solar system's early history, which we read from cometary spectra and asteroid samples and meteorite analyses, is being continuously supplemented by trace amounts of material from completely different stellar environments. And it means that the boundary between our solar system and the broader galaxy is not a hard edge, but a gradient, a region where solar gravity gradually loses its hold and interstellar trajectories gradually become possible, through which material flows in both directions on timescales that dwarf anything relevant to human history. C/2026. A1 is almost certainly not an interstellar visitor. Its orbital characteristics connect it to the Kreutz family, which connects it to an event in our own solar system's history. Avi Loeb raised the question of a possible connection between this comet and 3 I/Atlas, evaluated the evidence, and dismissed the connection on the grounds of size discrepancy and orbital geometry incompatibility. That dismissal is almost certainly correct, but the fact that the question was raised at all, and that it was raised by someone with the credentials and the analytical framework to evaluate it seriously, reflects something real about the moment we are in. The category of objects with unusual characteristics that resist clean classification has expanded. The tools available to examine those objects have improved, and the conceptual framework that treats the solar system as a closed and fully understood environment has been opened by observation in ways that cannot be closed again. We are no longer simply observers of a system we believed we had largely mapped. We are participants in a traffic pattern that is older, larger, and considerably busier than any previous generation of humans had the instruments or the framework to recognize. The objects passing through our solar system right now include things that formed around other stars, travelled for unimaginable distances through interstellar space, and arrived here carrying chemical and physical records of environments we have never directly observed. We can detect them now. We could not before. And the number we'll detect in the next decade will almost certainly exceed the total number detected in all of human history before 2017. Oumuamua was supposed to be unprecedented. It turned out to be the first page of a chapter we are only beginning to read. Part 14. Solar observation is entering a new era. For most of human history, the sun was impossible to study directly. Not difficult, not inconvenient. Impossible in any meaningful scientific sense. You could look at it, briefly, painfully, at the cost of your vision if you were careless or persistent, but looking at something and studying it are entirely different activities. Galileo observed sunspots through darkened glass in the early 1600s, sketching their positions and tracking their movement across the solar disk with the careful patience that defined his entire scientific practice. The practice contributed to his eventual blindness. He understood that the sun was doing something interesting and structured. He had no way of understanding what it actually was, because the instruments required to answer that question would not exist for another 350 years, and the theoretical framework required to interpret the answers would not exist for most of that period either. For centuries after Galileo, solar observation remained constrained by the same fundamental problem. The sun is the brightest object in the sky by an enormous margin. Every instrument designed to observe other astronomical objects, telescopes, spectrographs, photometric detectors, must be modified, filtered, or operated in specialized ways to observe the sun without destroying itself or the observer. And even when those modifications were made successfully, the Earth's atmosphere introduced its own distortions. The turbulence of air moving in columns of different temperature and density, the same effect that makes stars twinkle, blurs fine detail on the solar surface in ways that set a ceiling on the resolution achievable from the ground, regardless of the quality of the optics. You could observe sunspots. You could observe large-scale surface features. but the fine structure of the magnetic field, the dynamics of the corona, the detailed behaviour of plasma on scales relevant to understanding flares and eruptions, these remained out of reach. The first significant change came with the development of the coronagraph in the 1930s. The French astronomer Bernard Liot constructed an instrument that artificially replicated the conditions of a total solar eclipse, blocking the solar disk with an occulting disk inside the telescope and suppressing scattered light with a series of precisely designed optical components, allowing the corona to be studied in detail for the first time without waiting for the moon to cooperate. This was a genuine breakthrough. The corona, previously observable only during the brief minutes of totality in the path of a solar eclipse, became accessible for sustained, repeatable, scheduled scientific observation. Its structure, its temperature, its dynamics, these became subjects of ongoing research rather than occasional opportunity. The next transformation came from space. Removing a telescope from Earth's atmosphere eliminates the turbulence problem entirely. Space telescopes observe the Sun from above the atmospheric ceiling that limits ground-based resolution, and they can be designed to operate continuously without the interruptions of night, weather, or seasonal geometry. The Solar and Heliospheric Observatory, SOHO, launched in 1995 as a joint project between NASA and the European Space Agency, positioned at the gravitationally stable point between Earth and the Sun, where it could maintain a continuous view of the solar disk and the surrounding space. Its coronagraph, blocking the solar disk to observe the surrounding corona, became one of the most productive instruments in the history of solar observation almost immediately. It detected solar wind structures, tracked coronal mass ejections from eruption to interplanetary space, and discovered thousands of comets that no ground-based instrument had ever seen. Sungrazers too faint and too close to the Sun to be visible from Earth, detectable only from SOHO's unobstructed vantage point above the atmosphere and away from solar glare. Over 3,000 Kreutz sungrazers in the catalogue, the majority of them SOHO discoveries, represent a direct product of that continuous vigil. The Solar Dynamics Observatory, launched in 2010, pushed the capability further. SDO was designed specifically to observe the Sun across multiple wavelengths simultaneously, capturing the solar surface and lower atmosphere in ultraviolet and extreme ultraviolet light that reveals magnetic field structures, plasma temperatures, and dynamic phenomena invisible in ordinary white light. Its imaging cadence, one complete set of multi-wavelength solar images every 12 seconds, continuously without interruption, produced a dataset of solar behavior that transformed the field. For the first time, researchers could watch the full life cycle of solar flares, filament eruptions, and coronal mass ejection initiation events in real time, with enough temporal resolution to follow the detailed sequence of magnetic and plasma dynamics that produced them. Events that had previously been reconstructed from sparse observations became fully documented processes. The physics that had been inferred became observable. But both SOHO and SDO, transformative as they were, operated with limitations that the current generation of instruments is specifically designed to overcome. SOHO's coronagraph produces images at relatively low spatial resolution, sufficient to track large-scale coronal structures and detect comets, but not sufficient to observe the fine magnetic field dynamics in the regions where CMES initiate and where comet-corona interactions might produce detectable signatures. SDO's resolution, while high by the standards of space-based solar observation, is still limited by the practical constraints of building, launching, and operating instruments in the space environment. The Daniel K. Inouye Solar Telescope, DKIST, represents what happens when those constraints are lifted as far as current technology allows. Located on the summit of Haleakala, on the island of Maui, at an altitude of just over 3,000 meters, DKIST was built where it was built for specific reasons. The atmospheric conditions above Haleakala are among the most stable available for ground-based solar observation anywhere on Earth. The seeing, the technical term for atmospheric turbulence affecting image quality, is consistently good enough to support the kind of extreme resolution imaging the telescope was designed to produce. With a 4-meter primary mirror, DKIST is the largest solar telescope ever constructed. Its adaptive optics system corrects for residual atmospheric turbulence in real time, producing images of the solar surface with a spatial resolution of approximately 30 kilometers per pixel, 30 kilometers, on an object 93 million miles away. To appreciate what that means, consider that the Sun's diameter is approximately 1.4 million kilometers. The features Dickist can resolve are smaller than many cities on Earth, visible on a star at a distance that light takes 8 minutes to cross. The magnetic field structures that drive solar flares, the tangled braided configurations of field lines that store energy and release it catastrophically in reconnection events, can be observed at a level of detail that was purely theoretical before DKIST began operation. The first public images released from the telescope showed the granulation pattern of the solar surface, the convection cells where hot plasma rises, spreads, cools and sinks, with a sharpness that prompted solar physicists to describe their reactions in terms that science rarely uses. Several researchers, in public statements and interviews, used words like astonishing and emotional. One described seeing features they had spent careers modelling theoretically appear in an image with the clarity of a photograph taken nearby. That is what a factor of 10 improvement in resolution does to a field that has been working at the edge of its instruments for decades. For the April 4th perihelion of C/2026A1, the combination of DKIST, SDO, SOHO, and the Solar Orbiter mission creates an observational network without any historical precedent for this type of event. DKIST will be monitoring the solar surface magnetic field dynamics in the regions the comet approaches with resolution sufficient to detect fine-scale disturbances that no previous instrument could have seen. SDO will be providing its continuous multi-wavelength coverage of the full solar disk and corona, capturing the thermal and magnetic state of the solar atmosphere across the relevant wavelength range at 12-second cadence. SOHO's coronagraph will be tracking the comet's approach trajectory and recording the behaviour of the outer corona during and after perihelion, watching for any structural changes or disturbances in the coronal streamers that might indicate an interaction effect. And the solar orbiter, positioned at a different point in the inner solar system on its own elliptical orbit around the Sun, will be observing the same events from a different viewing angle entirely, providing a stereoscopic dimension to the dataset that single-vantage observations cannot replicate. What this observational network means in practical terms is that the question which has haunted the comet-corona interaction hypothesis since the 2011 event, the question of whether the available data is sufficient to distinguish a genuine interaction signal from background solar noise, has a different answer in 2026 than it had then. The 2011 observation was intriguing precisely because the instruments were capable enough to see something suggestive, but not capable enough to resolve it definitively. The gap between what was observed and what could be concluded was wide enough to accommodate both the coincidence interpretation and the interaction interpretation, without either one being falsifiable. That gap was not a failure of science, it was an honest reflection of what the instruments of that era could deliver. In 2026, the instruments are better. The coverage is more complete, the object is larger, and a larger object interacting with the corona produces a proportionally larger signal, more material, more plasma interaction, more potential for detectable magnetic disturbance if any disturbance occurs at all, and the data will exist regardless of the outcome. Whether the comet disintegrates cleanly and the Sun continues its independent activity without measurable influence, or whether something more interesting happens in the corona on April 4th, the multi-instrument record of what occurred will be available for analysis, reanalysis, and definitive interpretation in ways that previous sungrazer events could not support. For decades, we have been guessing about what happens when a comet enters the solar corona at close range. We have been extrapolating from incomplete data, arguing from limited observations, constructing models in the absence of the measurements needed to test them properly. On April 4th, the guessing ends. We will know more after perihelion than we do right now. And that, regardless of what the comet does, regardless of whether it survives or fragments or produces something completely unexpected, is exactly what science was built for. Part 15, Final Synthesis, what April 4th really represents. Let's take a step back from everything. The orbital mechanics, the plasma physics, the classification debates, the infrastructure risk assessments, the interstellar object comparisons, the Carrington event history, and look at what this moment actually is, stripped of the anxiety and the speculation, and the narrative weight that has accumulated around it over the past several weeks. A comet left the inner solar system approximately 1900 years ago. The world it departed from was organised around structures that no longer exist in any recognisable form, empires whose borders have long since dissolved, cities whose names have changed beyond recognition, belief systems that have transformed so thoroughly across the intervening centuries that the people who held them would find our world as incomprehensible as we would find theirs. When this comet last rounded the Sun, the most sophisticated optical instrument a human being could construct was a polished piece of metal. The concept of a solar system, of planets orbiting a star rather than heavenly bodies circling a fixed Earth, was not just unknown but actively contrary to the dominant cosmological understanding of the time. Nobody watching the sky in that era, if they saw anything at all during the comet's previous perihelion pass, had any framework to understand what they were seeing in terms that we would recognise as scientific. The comet did not notice any of this. It rounded the Sun, whatever happened during that pass went unrecorded or unconnected to this object, and it continued outward into the solar system on the trajectory that gravity had assigned it at the moment of its creation, or more precisely at the moment its ancestor fragmented and distributed its children across a range of orbital paths that would carry them back to the Sun on schedules spanning centuries and millennia. This particular fragment drew the long orbit. 1900 years is a long orbit. It carried the comet out past the planets, past the outer reaches of the planetary system, into the cold, dark region where the Sun is just the brightest star rather than the overwhelming presence it is in the inner system. And then gravity, patient and indifferent, began pulling it back. For 1900 years, nothing of significance happened to it. It experienced no meaningful force except the slow gravitational curvature that defines its path. Time passed for the comet only in the sense that the universe around it continued its own processes. The Sun converting hydrogen to helium at its core, the planets completing their orbits, civilizations rising and falling on a small rocky world whose existence the comet had no way of registering. The fall of Rome did not affect its trajectory. The invention of the printing press did not alter its velocity. The Copernican revolution, the development of the telescope, the scientific method, the Industrial Revolution, the nuclear age, the space age, the information age, all of it happened while the comet moved through absolute darkness, carrying its frozen record of the early solar system in complete indifference to the species that would eventually be watching when it returned. And now it is here. It has arrived on schedule, on the trajectory it has always followed, at the one moment in its entire 1900-year circuit that coincides with something genuinely unprecedented in the history of solar observation. It is arriving when we have a 4-metre solar telescope on a Hawaiian mountaintop, capable of resolving features on the Sun's surface smaller than a city. It is arriving when a spacecraft positioned between Earth and the Sun has been watching the corona continuously for 30 years and has catalogued thousands of its predecessors. It is arriving when a dedicated solar observatory satellite is capturing the full disk of the Sun across multiple wavelengths every 12 seconds without interruption. It is arriving when a second spacecraft in a different orbital position can observe the same events from a completely different angle, providing stereo coverage of a solar encounter that previous generations could only observe from a single terrestrial vantage point. It is arriving when a planet full of people can follow the event in real time, on devices small enough to fit in a pocket, communicating instantly with each other and with researchers who are watching the same data streams. If this comet had reached perihelion in the year 500 of the Common Era, nobody would have known what it was. They might have seen it, a brightening near the Sun in the days before perihelion, a tail visible in the evening or morning sky in the days after, an unusual apparition that prompted interpretation through whatever cosmological framework the observer's culture provided. They would not have known its composition. They would not have known its orbital period, or its membership in a family of fragments from an even larger and older object, or its relationship to the solar activity that preceded or followed its passage. They would not have been able to distinguish the effects of its corona passage from the background behaviour of a star they lacked the instruments to monitor in any meaningful way. The event would have happened, been noted or not noted, interpreted or misinterpreted, and moved on. The comet would have continued outward into the darkness, and the moment would have closed without producing the kind of durable, testable, cumulative knowledge that defines scientific understanding. We can do something completely different now. Not perfectly. The uncertainties described throughout this entire story are real, and the limits of our predictive capacity are genuine and worth acknowledging honestly. The size of the nucleus is uncertain. The subgroup classification is unresolved. The question of whether a comet-corona interaction can produce measurable solar disturbance remains, at the time of writing, an open hypothesis rather than a confirmed mechanism. The outcome on April 4th is genuinely unknown, and anyone claiming confident predictions about what will happen is overstating what the current science supports. But we can observe what actually happens with a precision and completeness that would have been incomprehensible to any previous generation of humans who looked up at a strange light in the sky and tried to understand it. We can measure the comet's behaviour in the corona. We can record the solar magnetic field response. We can correlate the timing of any subsequent activity with the passage of the comet through the most sensitive regions of the solar atmosphere. We can, for the first time in the history of Creutz's sungrazer observation, collect data sufficient to actually answer the questions that previous events only raised. There is no direct threat to Earth from this comet. That statement has been made throughout this series, and it bears repeating one final time clearly and without qualification. The comet will not hit Earth. The CME risk, real as it is in the context of solar maximum, is not meaningfully elevated by the comet itself, beyond what the Sun is already fully capable of producing through its own internal dynamics. The Ohio fireball was a coincidence, a real event correctly reported, unconnected to the solar activity and unconnected to the comet. The clustering of events in the late March and early April calendar is a product of human pattern recognition operating on independent phenomena during a period of naturally heightened solar activity. The universe is not targeting us. It is simply doing what it does, and we happen to be paying attention at a moment when several interesting things are occurring in proximity to each other. What April 4th actually represents, when the anxiety is set aside and the event is seen clearly, is something considerably rarer and more valuable than a threat. It represents a scientific opportunity that has not existed before in this precise form, and may not exist again in this precise form within the professional lifetimes of the researchers currently preparing to observe it. A relatively large Kreutz sungrazer, larger than the typical SOHO detected fragment, early enough in its detection that extended observation has been possible, unusual enough in its classification to raise genuine questions about the completeness of the Kreutz family map, is arriving during solar maximum, during a period of active solar monitoring, with the full complement of modern solar observation instruments pointed at exactly the right place at exactly the right time. Whatever happens during those hours will produce data. That data will contribute to understanding comet composition, corona interaction physics, Kreutz family structure, and the relationship between cometary passages and solar activity in ways that no amount of theoretical modelling can substitute for. The data may confirm existing models, it may challenge them, it may produce results that require entirely new frameworks to explain. All three of those outcomes are valuable. All three advance the field. There is also something worth holding in the human dimension of this event that has nothing to do with data or models, or professional scientific advancement. Every person who looks up in the days around April 4th, who follows the tracking updates, who reads about what the instruments are seeing, who stands outside on a clear evening and looks toward the western horizon in the hope of seeing a tail, is participating in something that is genuinely as old as human consciousness itself. We have always looked up. We have always tried to understand what we saw above us. The tools available for that effort have changed beyond recognition, from the naked eye observations of antiquity to the adaptive optics-corrected 4-meter mirror of DKIST. The theoretical frameworks have changed from mythology to physics. The precision of the descriptions has changed from poetic to quantitative. But the fundamental impulse to stand on a planet, look at a sky, and reach toward comprehension of the scale and nature of what surrounds us has not changed at all. It has not changed because it is not a learned behaviour or a cultural artefact. It is something closer to a defining characteristic of the kind of creature we are. An ancient object is meeting a civilization that has spent its entire existence trying to understand the sky it lives beneath. The meeting lasts only hours. It has been 1900 years in transit, and for the first time in the long unbroken history of humans watching strange lights near the sun and wondering what they meant, we are genuinely equipped to find out. That is not a threat. That is not a coincidence. That is science doing exactly what it was built to do, turning the unknown, one careful observation at a time, into something we can finally understand.